Well, I'm delighted to be here to help celebrate Vijay's birthday. I've known Vijay since he was a student in my combinatorial algorithms course at Berkeley, and he short-circuited the course and earned his grade by proving the wonderful results with Silvio McCauley about matching in graphs. And he's gone on to wonderful work on satisfiability, on many different wrinkles of variations of the matching problem, on algorithmic game theory, advertising, economics in general, questions of stability and equilibrium in economic systems and so on. So Vijay has moved with the times and continues to be incredibly productive. I'll have some anecdotes tonight, but I'll reserve them for later. Listening to the other speakers and looking at the list of topics, I realized that what the organizers were looking for was something broad and speculative, and I had sent them slides for a very detailed technical talk. So what I'm going to do on the fly is to zip through some of the slides and completely truncate the particular technical talk that I was going to give, and then move on to some broader observations and questions. So first of all, this is joint work with Manuel Torres, who was a visitor from to Berkeley from Irvine a couple of years ago and did this work with me. Manuel has gone on to great work at the University of Illinois. Maybe it's this one. So the famous Steiner tree problem on a graph is the following. Within a given n-vertex edge-weighted graph, you want to find a tree with a minimum sum of edge weights that includes a set of required vertices. I'm going to talk about a version in which instead it's called the group Steiner problem. And now each vertex of the graph carries a color. And you're required to find a tree of minimum sum of edge weights. But now, instead of having required vertices, you only have to include within the tree at least one vertex of each color. There are various applications. In view of the shortage of time, I will skip over these. A lot is known about the complexity of the group Steiner tree problem. It's polynomial time approximable on a graph within a factor of log squared n, and not within an appreciably smaller factor unless some very unexpected result in complexity holds. So we have a pretty good understanding of the worst case approximation ratio for the problem. I'm going to concern myself in this talk with rectilinear problems where the vertices are points in the plane and the distance is just the Manhattan distance. It's known to be NP complete. There's a polynomial time approximation scheme with running time exponential and 1 over the approximation ratio, so the degree of approximation. So in fact, this p-TAS is not really usable in practice because of the very severe dependence on epsilon. But in practice, rectilinear problems can be solved not for the group Steiner problem, but for the regular Steiner problem. It can be solved very simply by starting with a minimum spanning tree and adding Steiner points at the intersections of some Steiner tree edges. That tends to give a very good approximation. I'll further restrict the problem by assuming that the graph is a grid with each cell of the grid containing a single vertex of a particular color. And a perfect solution will be defined as a connected subgraph containing exactly one vertex of each color. And our focus in this part of the talk will be to solve this decision problem of deciding whether there's a perfect solution, a connected subgraph containing exactly one vertex of each color. And now I'm going to radically skip parts of the talk. Let me just say that there is a very good dynamic programming algorithm when the number of colors is small. There's a linear size integer programming formulation. And the main burden of this part of the talk is a heuristic algorithm for solving the problem. And I'm going to, in lieu of the discussion I had prepared, I'm going to rely on an example which is more or less canonical. So what we have here is a rectangular matrix with a, as it happens, a letter. In generality, it would be a color in every cell of the grid, of this rectangular grid. And what we want to find within this is a connected subgraph of the grid which contains exactly one vertex of each color, exactly one copy of each of the letters occurring. So here it is. We've somehow been able to search through this grid, and marked in red, we have the letters that comprise the solution connected in the L1 sense, where each vertex is adjacent to its north, south, east, or west neighbor. And this is the structure they were trying to find. And what I want to do is present a heuristic algorithm for this particular problem of finding a perfect solution when it exists, and tell you about some of the results, and then branch out more broadly to talk about how we evaluate algorithms. So the first step in this heuristic algorithm is to look at the colors that occur least frequently in the instance. And the intuition here is that these are the colors that give you the least flexibility in choosing a representative of the color. And so we want to do this as well as we want to place those representatives close together as best we can, because they produce the greatest influence on the liberties that we can take with the remaining colors. The remaining colors have higher frequencies and will be easier to deal with. So in this particular case, the infrequent colors are W, G, V, Y, L, N, and V. And a search tailored to the case where the number of colors is small reveals that the best solution that can be obtained for placing those colors is the one shown in red. It minimizes the total number of additional cells that have to be added. That number is called the gap. The number of cells that have to be added in order to include these particular cells in a single connected structure. So the first step is to place these, to choose a representative of each of the infrequent colors so as to reduce the gap, which is the number of extra cells needed to connect those copies of the colors. The next step, which isn't really adequately explained here by this picture, is to go through the remaining colors, building upon this partial solution, take each of them in turn in increasing order of frequency, and place each of the in place and choose a representative of each of those colors in turn, choosing the representative which is closest in a certain sense to the connected structure that has been created so far. There's a technical sense of what I mean by closest, which I will skip in this truncated version of the talk. So we go through, and what we end up with at this point is is a structure which contains exactly one copy of each color, but which may not be connected. And here we see that it fails to be connected because there's a space or a partial gap separating the occurrence of the letter G from the rest of the structure. So here we have a partial solution with a gap of 1. 1 is the number of additional cells that have to be used to connect the structure. The final stage in the process is to close the gaps, if possible. And this is done by swaps, in which we take the original solution at this point, containing exactly one occurrence of each color, and then look for swaps which reduce the gap, or if there are none that reduce the gap, keep the gap the same. So in this particular case, we end up performing swaps, each of which either retains the original gap or reduces it. So in this case, the swaps would first insert an O as indicated, removing an O from a letter O elsewhere, then inserting an F, then inserting a D. And by this series of swaps, get a connected structure containing exactly one occurrence of each color, and therefore solving the instance. Now, it turns out that I have no theorems to back this up, but empirically, this process works well. The evidence that it works well is that we generated random instances with a planted perfect solution. So you start with specifying a frequency distribution of the colors, and then choose a particular placement where you can insert a perfect solution, a connected subgraph, randomly chosen, and with the colors randomly assigned in one-to-one fashion to the vertices of that subgraph, so that it becomes a solution. And the rest of the network is left alone. So you take a random instance with given color frequencies, perturb it by planting a perfect solution. Then the question is to find that perfect solution. And the evidence that the algorithm is good, well, I'm going to skip lots of stuff, I guess everything. The evidence that that solution is good is that with a fairly high frequency, we actually succeed in recovering a perfect solution when one has been planted. So briefly, in each experiment, the dimensions of the grid, the number of colors, and the frequency distribution of the colors are chosen. 1,000 instances are drawn. In each case, a perfect solution is planted. And we find that in each experiment, where the experiments differ according to the frequency distribution of the colors, the frequency of finding a perfect solution exceeds 90%. And there were some refinements of the algorithm that could be used to push this 90% higher. So now I want to turn, having quickly gone over this example, to more general considerations. How can theory help us to decide when we have a good algorithm, an algorithm that can be used in practice? Would it be the worst case complexity? Would it be the quality of a worst case approximation? Or would it be something else? And so what I'd like to do is not to answer this question, but to pursue it through a number of examples to see how we feel about the question. So let's think about the simplex algorithm of linear programming. Raise your hand if you think it's a good algorithm. Well, it doesn't have polynomial time complexity. There are examples where the running time of the simplex algorithm is exponential. On the other hand, in practice, on instances that actually arise, it seems to solve the instance very rapidly. The only theoretical result I know of that tends to support the practical efficiency of the simplex algorithm is the following result by, I think, Teng and Spielman, where they show that if you take any instance of the problem and perturb the solution, perturb that instance locally, then you will very likely, with high probability, you'll get an instance that the simplex algorithm will handle well. So in other words, the bad examples are isolated singularities rather than generic. So I'd say that the simplex algorithm is good, but its reputation in complexity circles, well, we now have other polynomial time algorithms for the linear programming problem. So the problem is in P, but the simplex algorithm is not a good algorithm by the strict standards of complexity theory. Should we worry about that? I don't know. Let's look at a few other examples. What about the asymmetric traveling salesman problem? This is the traveling salesman problem where the edges are directed rather than undirected. What do we know about it? In practice, methods based essentially on linear programming get very good approximate solutions very rapidly. The theoretical result, the recent theoretical result, which is widely celebrated, is that we can get a constant factor approximation, but with a very large constant factor. So would you say that this is a good algorithm from the point of view of theory or not? I won't ask you to vote, but clearly we see some distance between what occurs in practice and what theory can tell us. What about neural networks for deep learning? Are the problems related to supervised classification using deep neural nets efficiently solvable or not? Well, we're very far from having any theoretical explanation. But in practice, there's evidence that the deep learning schemes give good solutions. So I guess what we have to say there is that we really need to have a theoretical explanation. We really need to understand why it appears that with, at least with fairly large training sets, the deep learning schemes will succeed. What about stat solvers? Is the satisfiability problem easy or hard? Well, it's complete in NP, so we have to assume that from viewpoint of complexity theory, it's hard, but people in digital design or theorem proving who encounter satisfiability problems and solve them routinely consider a SAT problem to be easy because the instances that occur in those domains of application tend to fall apart. Furthermore, through the work of Kevin Leighton Brown, we have a very detailed understanding of which strategies for the satisfiability problem work best according to some parameters that describe the structure of the instance. So a lot is known about how those instances can be solved, and there's a lot of predictability. What about matrix multiplication? What do we know about the complexity of the matrix multiplication problem? Well, there are, of course, there are easy examples that solve it in time order n cubed. Strassen's algorithm, which is pretty nice, solves it in something like order n to the 2.8. But the world champion algorithm is due to Coppersmith and Winograd, and has a running time which is big O of n to the 2.38, something like that. But the constant hidden by the big O is enormous. One would never use this algorithm in practice. So again, we see that there's a discrepancy between the algorithms that are sanctified by theory, which tends to disregard the constant in the big O, and what we see in practice. Matrix multiplication for dense matrices you would never use the so-called theoretically best algorithm known to solve these problems. Another example is sorting networks. So these are networks of comparators that take an array of n numbers and pass them through this network of comparators to put them out in increasing order of their values. There are very simple sorting networks due to Batcher and others, which have about n log squared n comparators and have a very simple structure. And from the point of view of pure theory, there's the AKS algorithm, which is an n log n algorithm, but is extremely difficult to describe. And again, would never be used in practice. Integer programming. Integer programming is NP hard, but for certain classes of problems, it works very well. Dan Gusfield has made the following remark. He says, always try integer programming, it might work. Well, that's something. I mean, if you have an instance and it'll solve the instance for you, then despite the theoretical hardness, it becomes useful. And in fact, there are certain problems where experience shows that integer programming knocks them off very easily. So if you want to solve Sudoku, you simply write to the constraints of the Sudoku problem as a set of linear integer constraints, which is easy to do, and put them into any respectable integer programming solver, and it will very rapidly solve the Sudoku problem. So these are just a bunch of examples to raise the question, how much can the results of theory based on worst case solutions or worst case approximate solutions guide us. It seems in the case of approximation algorithms that very often the worst case approximation ratios for polynomial time algorithms are pretty high, and yet the problems can be solved easily. So there's a kind of loss of trust between the practitioners and the theoreticians in such cases. One computational biologist said, why should I listen to the theoreticians who solve the problem within a factor of log n when my students will solve it within 1%? So again, we have a dilemma as to how to evaluate a particular problem. So I just thought that I would leave these as open questions. Certainly the elegant results of theory, even if the big O factors are huge, deserve great respect. But practitioners will still have to look to their empirical results to decide what to do in practice. So I'll leave you with that question and see if there are any questions.
Questions?
Yeah.
Would you be brave enough to suggest an answer?
Well, there are things that one can do. Sometimes, in some cases, it's possible to put a condition on the instance or on the structure of the instance, which will guarantee that even though the problem is NP-hard, the instances of that type are easy. So that was done for clustering problems by people at Stanford recently, and Stanford and CMU, and that gives some guidance. Basically, they show that if all of the nearly optimal solutions to the clustering problem have great similarity in their membership, then simple algorithms will actually find optimal solutions. So more work along those lines, characterizing subclasses of instances, would be one way to go. Yeah.
Ruta.
Do you think theory has guided the algorithms that work well in practice?
Well, in general, has theory guided algorithms that work well in practice? In general, I would say yes, but one has to sometimes make extrapolations from the theoretical results. So, for example, it's been found that primal dual methods in linear programming are a powerful approach to getting good approximation algorithms. But the theoretical versions which give particular results need to be tinkered with considerably in order to get the best practical results. So it seems that that the insights can come from the worst case theoretical framework, but often have to be modified in order to get performance. Yeah.
Talking about simple algorithms versus approximation algorithms, that's one thing. But when we talk about solving instances using IP,
Yeah.
integer programming, I think there's a kind of danger in going down a path. So, for example, you have a practical problem, you solve it using integer programming, and you're done. You're very happy. And then 2 years down the line, the problem becomes a little bit more difficult, and maybe you can't solve it very well.
Yeah.
And then you have this opportunity cost of time where you haven't thought enough about the problem and got the insights.
Mm-hmm.
And that's something that also a point that we as a community.
I see. You're saying that the advantage of the theoretical approach, which allows instances to be arbitrarily big and to study the problem in terms of functions of the size of the input, what its findings have greater generality, whereas empirical work inevitably is limited because you've had to pick a particular instance size. Yeah.
There are no insight from the program, but you might learn something about the problem structure and realize that this structure is using code.
Right.
I'm really channeling the Jay.
Right. But in some cases, as in deep learning, where you're solving supervised classification problems, it seems that the current state of the art is to, we don't have the general theorems. All we have is the empirical evidence. Yeah. Way back
One
there.
last question, Moses.
Moses, yeah.
I want to ask you about traveling there.
Yeah. Yeah.
The relaxation came up with what were your hopes for that when you worked on that?
Right. So with Michael Held, I worked in the 60s on traveling salesman problem. We didn't view it exactly this way, but the way it's currently viewed, you solve a linear programming relaxation and then use that as a starting point for modifying some dual variables, which will move you in the direction of a perfect solution. The way we looked at it was a little different, although theoretically equivalent. that the problem remains unchanged, where you add a constant to the positive or negative to the costs of all the edges incident with a particular node. And you have the freedom to juggle those constants. And so basically what we did was to give an algorithm which kept juggling those constants, which are really like dual variables, in order to drive the minimum spanning tree to one where you have all degrees 2, or where you don't have any high degree nodes. So we were happy just to gain the world championship for a short time by solving bigger problems than had been solved before. But then cutting plane methods came in and far superseded what we had done, and in the hands of people like Bill Cook and Applegate and Václav Kvatel, they were able to solve problems with tens of thousands of cities and using months of computer time, and get results far surpassing ours. So I don't know exactly what we were looking for. I guess we were locked in a competition with people using other heuristics around the same time, and we were driven with the desire to beat the other people. That was as far as our aspirations went.
Let's thank Dick once again.
Okay.